Hello, welcome back. We will continue our discussion of Unit 1, alcohols, ethers, and epoxides. I'm pretty excited about this unit. It's our first unit in Organic Chemistry 2, and B, using a new laptop with a new headset, and I have a new haircut, and fresh start. I know Organic 1 can be quite shocking, quite a jarring experience, but hopefully you have the right foundation, and then Organic 2, we're just going to build up or build on that foundation, and at times it's going to seem very easy. We're using the same concepts over and over again in terms of reactions and reaction mechanisms. And for this video, we are going to start with some reactions, or we're going to look at our first reactions in the alcohol chapter. So the reaction we're going to look at first is to convert alcohols into alkyl halides using substitution, and hopefully you remember what SN1 and SN2 are, and we could do this via a whole host of different reagents. Okay. Yeah, let's just get right into it. And I'm going to note my reactions A, B, C, D, etc. So we'll start with reaction A, and we're going to call this alcohol substitution with HX. That could be HCl or HBr. And honestly, we should divide up their alcohols into two sets. And the first set, I should have put it up here, secondary or tertiary. Okay. In our first video in this unit, we talked about classifying alcohols, primary, secondary, and tertiary. Now is when we're going to use that information. Because if your alcohol is secondary or tertiary, and you are doing a substitution with HX, yes, your mechanism will be SN1. Why do I say that? Secondary and tertiary alcohols can turn into stable secondary and tertiary carbocations. Okay, let me show you the overall reaction, and when you see the mechanism, this will be pretty clear. Let us take this secondary alcohol, OH. We're going to use HBr. And the product, okay, is this. Substitute the OH for a Br, but the Br can come from the front or the back. Okay, I'll explain this when we look at the mechanism. But you know what this is called, right? When you have a mixture, and it is a 50-50 mixture of enantiomers, remember the term racemic? Racemic mixture. Okay. Let's look at the mechanism. And we are going to follow an SN1 type of mechanism. We're going through the carbocation. What's going to happen first is we're going to protonate the alcohol, or protonate the hydroxyl group first. Some professors like to use equilibrium arrows. For me, it doesn't really matter. For my class, I would just go ahead and write a regular arrow. Okay, you know, proton transfers are typically reversible. That's why some people would like to use equilibrium, but again, for me, it doesn't matter that much. Oh, shoot. Also, when students draw the mechanism for me, I don't care about stereochemistry. Okay, but in the fill in the products, I typically do care about stereochemistry because I want you to know that you literally make two different organic molecules. They just happen to be enantiomers. Okay. So you don't have to draw that S dash, and I'm not going to draw that S dash anymore. We protonate the hydroxyl group. make the carbocation. So now this leaves, and we'll talk about the details after we get this down on paper. But you do know carbocations are flat. That carbon is sp2. sp2 atoms are trigonal planar, flat. Also, I'm a little bit of a stickler. I want you to draw every product that's made in each preceding step. Okay, so we did produce a Br minus through this arrow. Okay, through this arrow, the Br minus is not involved, but we did produce what? Water, H2O. Okay. The last step in this, it looks like 3-step mechanism, is go ahead and add the Br minus. Nucleophile, Br minus, attacks electrophile. Again, with mechanism, for me, you don't have to indicate stereochemistry, right? And the way you draw the green arrow, it's not supposed to imply front or back anyway. Okay, you could have drawn the green arrow coming from the bottom, and it would still give me the same product. Okay. What can we label with a mechanism? We could label the rate determining step. For substitution reactions, do you remember that the rate determining step, the slow step, is the step where the leaving group leaves? That's your leaving group. It left. This is your RDS, rate determining step. Now, this is a little bit different than alkyl halide substitution, right? Pretend we had a chlorine here. If we're doing an SN1, normally that chlorine will pop off by itself. But you notice that this isn't popping off immediately. We have to protonate it. We have to protonate it. The phrase you want to memorize is OH is not a good leaving group. That's why this is a step longer than most substitution, SN1 substitutions that you know, because we have to make it a good leaving group. So if OH is not a good leaving group, water is, H2O is. We converted the hydroxyl group into a good leaving group. Because if this was to leave on its own, you would create OH minus. A negatively charged molecule is typically less stable than a neutral molecule. So here, there's a lot of motivation to kick this out, right, to get this oxygen to be neutral, to make it H2O. There's not really a lot of motivation for this to leave by itself to make OH minus, right? We don't want to typically create charged products. Here, we take a charged starting material, and then we made a neutral product. Remember those two phrases? Because that is a theme for all of these reactions that deal with alcohol substitution. Okay? That is reaction A via SN1. What do you suppose reaction B will be? Reaction B will be primary alcohol substitution. It's good that we're going to try to get this on the same page so we can compare side by side the SN1 and SN2 of alcohols. We are still going to use HX, but now we're going through a different pathway, SN2. What's the easiest way to explain why it's SN2? It's primary. Primary carbocations are very unstable, so we are not going to go through the carbocation via an SN1 process. We're going to avoid making a primary carbocation by doing SN2. The nucleophile will attack as the leaving group leaves, so we'll never have a naked carbon, a carbon with only 3 bonds. Let me show you that reaction. Now it's primary, so this Let me just double check. I'll put a branch here. It doesn't matter, but make it a little more interesting. It's still primary, right? That dot is connected to oxygen, and that dot only is connected to one other carbon. We're still going to react it with HX, and let's use HCl now. Okay. HBr or HCl is fine. That carbon is not chiral, so when you do your substitution, there shouldn't be any wedges and dashes. No wedges and dashes. But I know those of you who did really well in Organic 1, you know that SN2 proceeds with inversion. But remember, you only observe the inversion, right, when your carbon is chiral. Okay? We have no idea how this chlorine added, whether it's the same side or opposite side. Backside attack is what we called it before, right? Relative to this OH. We can't tell, but it does come from the backside. Enough about that mechanism. The fact of the matter is that OH is still a bad leaving group. So we still have to go through the process of making it a good leaving group by protonating it. I'm going to shorthand this, and that's perfectly fine, OH2, but remember it's positive now. And also we kicked out a chloride, and we're going to use it in the next step. Because we're not going to wait for the leaving group to leave on its own, like we did for SN1. We're not going to wait to make a carbocation. We're going to immediately attack that carbon, one with a dot, and we'll show the leaving group being kicked out. And that's your product. Okay, so it's shorter, a shorter mechanism, because we're not waiting for the leaving group to leave on its own. Right? And the leaving group is still water. Your RDS is when the leaving group leaves, RDS. By doing this, we avoid a primary carbocation. I don't envision me drawing ever a primary carbocation in Organic 2 or Organic 1. Okay. Those are two reactions. If we zoom out, you have one study sheet for SN1 and SN2, SN1 reaction A, SN2 reaction B. Okay. But we have other reagents. We have two special reagents, thionyl chloride and phosphorus tribromide. And I think we'll have time to talk about tosyl chloride as well. But our next reaction will focus on SOCl2 and PBr3. This will be reaction C. And these are special reagents to convert alcohols into alkyl halides. Let's see. Now, how do I want to title this? Okay. Let's say special reagents. To convert a little bit long. Special reagents to convert alcohols to alkyl halides. Let's use a secondary alcohol. And yes, I will put some stereochemistry. The first reagent that I want to look at is thionyl chloride, SOCl2. It's spelled thionyl chloride. The substitution proceeds via SN2, and knowing that, hopefully you can predict that you get this molecule here, the chlorine, because it's SOCl2. Let me note that this is SN2. Let me show you now phosphorus tribromide, and we'll use a tertiary carbon, a tertiary alcohol. How do I want to draw this? Okay, that's definitely tertiary, and it is chiral. Okay, we can even put the asterisks. I sometimes ask students to mark the chiral carbons with an asterisk, and this is definitely chiral. When we use PBr3, phosphorus tribromide, it still proceeds with inversion. And the easiest way to draw that is you keep your lines to lines, and then the BR comes from the front, because that's the backside of the dash. If the BR is coming from the front, it's pushing the methyl group to the back. Remember inversion? It's like when a gust of wind inverts your umbrella. Same thing here, a gust of wind came this way, and it pushed this bond to the back, the methyl group to the back. This is SN2. The thing is, if you use SOCl2 or PBr3, it is always SN2. So primary, secondary, tertiary alcohols go via SN2. So all alcohols do SN2 with these special reagents. Now, your phosphorus tribromide mechanism is in the textbook. I'm not going to do that one. I'm going to do thionyl chloride, which is also in your textbook, and it's pretty unique. And there's a reason why people love doing this chlorination with thionyl chloride as opposed to using HCl. Okay, so we could have done this reaction also with SOCl2. Okay. Let's take a look at the mechanism, and then I'll explain why people like using thionyl chloride. Okay, no stereochemistry for a mechanism. We're going to have to make this into a good leaving group. That's always the case with substitution of alcohols. And thionyl chloride looks like this. If you look up the mechanism online, there are many or several methods. Oh, definitely that's not one of them. Ugh. Yikes. Opposites attract. That sulfur is partial positive. So oxygen is attracted to, whoops, this sulfur. Okay, try to make it point to the atom and not the bond. And then the variation of the mechanism that I'm showing kicks out the chlorine in the first step. And we have this. If I'm going too fast, and I'm pretty sure I am, because I could barely keep up with myself, go ahead and pause the video. Okay, I think that's right. Those are the products according to my two mechanism arrows. Don't forget the plus charge on the oxygen. Some mechanisms say go ahead and do the attack now, which is fine, because it's SN2, right? So there's my attack, and here's my leaving group leaving. And I want to draw it this way. Okay, I know it's a little bit complicated. Again, there are several variations online. And the truth of the matter is, the real story is probably a combination of all of these different methods, okay, different pathways. But all the pathways are going to be SN2. Okay, nucleophile attacks, leaving group leaves. But there's my product, right? So I'm done there. What about my other products though? This is where it gets a little bit interesting. If you follow your arrows, or my green arrows, you'll realize that you have this Cl minus. Okay, right? That Cl is from the one that got kicked out. There's one last step, and if you're in my class, I would require you to show this. Go ahead and deprotonate the SO2. My Gen Chem is a little bit weak. I think that's bent, right? Because we have a lone pair for this sulfur. 1, 2, 3, 4, 5, 6, and it's neutral. Okay. So let me just finish this. Look what we get. We get HCl for sure, and we also get sulfur dioxide. Right? Sulfur dioxide. That's a gas. Okay. Chemists like this reaction because it's high yielding. It's high yielding because we produce a gas, and there's no chance for the reaction to go backwards. Most organic reactions are reversible, right? And you get a mixture of starting material and product. But if one of your products is a gas, then that will escape and it cannot be reincorporated and go backwards. Another reason why people like this and why it's favorable is, if you remember from Gen Chem, producing gas is a production of more entropy, more disorder. And the universe naturally goes towards disorder. Most reactions where you increase the entropy, those reactions are typically favorable for the product. Okay. All right. So that is SOCl2. All right. And I'm not going to do PBr3. The next reaction, the last reaction for this video, I'm going to try to squeeze in reaction D. And I'm going to introduce it here. Later on, we're most likely going to use it in some synthesis problems. This is a reaction called tosylation. And the purpose of tosylation is to make OH a good leaving group again. Tosylation is this. We have an alcohol, and I'm just going to use a very simple alcohol, ethanol, plus this kind of complicated molecule. Please pause the video if you need time to copy that. Oops. That. There's a methyl group there. And what you get is something a little bit, convoluted, kind of scary, because we get this. But I'm going to show you how we can use nicknames for these molecules. Okay. Why? Why the heck would we want to do this? Because this is actually a very good leaving group. Okay. Let me give you some names. We call it, or I call it, most people call it, tosyl chloride. And what we're doing is we're installing what's called a tosyl group. Okay. If you look it up, this tosyl group is actually, I'll write it. It's equal to P. Don't worry about what P stands for. Toluene, sulfonyl chloride. Okay, a mouthful. But we're installing a tosyl group. Okay, a tosyl group. So this part right here is a tosyl. And you notice that it's just basically this molecule without the chlorine. So we're not going to draw the mechanism, but you can imagine that this oxygen comes in, hits the sulfur, and kicks out the chlorine. And then we remove this hydrogen in the last step. Why? Why are we doing this? Because this is called a tosylate. The whole molecule is called a tosylate. And tosylates are very good at substitution. And we could do substitutions in the next reaction. I'm not going to expect you to memorize the structure, at least my class. So let me give you the shortcut. The shortcut is this. OH plus, let's not use plus. No, I like to put the reagent on top of the arrow. The reagent that we're going to use is tosyl chloride, and you could abbreviate it TSCl. So these two are identical. Okay. And what are you doing? You're making that OH into an OTS, and that's the tosylate. So these two are synonymous, or these two are identical. Tosylate, tosylate, tosylate. The reason why you want to do this is you could do any substitution, and we're not going to have time to do some examples, but maybe we'll have time for some examples. For instance, if you want to do, you know what a good nucleophile is. Remember the cyanide nucleophile, CN-. Here's your dot, and that CN is going to come in and kick out the OTS. Okay, so normally for filling the product, you don't draw the secondary products, but I'm going to write it here to emphasize that that was the leaving group. I already told you that this is a good leaving group. So you're cutting it right here, right? Your nucleophile comes in at the dot, and you're kicking out what's called the tosyl group. This precedes good nucleophile, good leaving group. This proceeds via an SN2 reaction. Okay. All right, I got to leave this page, go on to the next page, but I'm going to give you a couple of phrases that will help you understand why we want to use tosylates, or why we want to do tosylation. Okay. First thing is, let's see. Tosylates. Substitute via SN2. So what does that mean? You're going to get inversion if your carbon is chiral. So remember inversion. And let me give you another example. So what if we have this? Okay, this one is going to go a little bit fast. OH, and I got to make it chiral. There. So it's a secondary alcohol. Okay. And I have the OH as a wedge. When you do your tosylation, okay, all you have to do is go back to our simple example. When you do your tosylation, you're not doing any reaction at the carbon right now. You're only changing that H to a tosyl group. So when you do your tosylation, the stereochemistry stays the same. And you make it a tosylate. Tosylate. The next step is when you do the inversion. The next step is when you use a nucleophile. So what's another nucleophile we could use? How about this one? SH minus, NaSH. Okay. Why did I say SH minus? Because you're supposed to know that this is ionic, and you split it up into Na plus SH minus. So you cannot forget the organic chemistry that you learned in the first semester. This is SN2, good nucleophile. This is a good leaving group. SN2 proceeds via inversion. So now we invert, put your nucleophile, and that's your product. We will come back to this. Why? Because there's going to be synthesis problems where we have to control the chiral carbon. Do we want inversion at the end, or do you want retention at the end? If we want retention, if we wanted SH as a wedge, we would have to use a different strategy. Okay. All right, that's good. That's 4 reactions, reaction A, B, C, and D. Definitely go back, make note cards or flashcards, or try to make like one-page study sheets, because those are the substitution reactions of alcohols. The next video, I believe we're going to do eliminations. So I was able to get all the substitutions onto this video.